Debris flows are geological phenomena in which water-laden masses of soil and fragmented rock rush down mountainsides, funnel into stream channels, entrain objects in the paths, and form thick, muddy deposits on valley floors. They generally have bulk densities comparable to those of rock avalanches and other types of landslides, but owing to widespread sediment liquefaction caused by high pore-fluid pressures, they can flow almost as fluidly as water. Debris flows descending steep channels commonly attain speeds that surpass 10 meters per second, although some large flows can reach speeds that are much greater. Debris flows with volumes ranging up to about 100,000 cubic meters occur frequently in mountainous regions worldwide. The largest prehistoric flows have had volumes exceeding 1 billion cubic meters. As a result of the high sediment concentrations and mobility, debris flows can be very destructive. Notable debris flow disasters of the 20th century involved more than 20,000 fatalities in Armero, Colombia in 1985 and tens of thousands in Vargas State, Venezuela in 1999. Features and behavior. Debris flows have volumetric sediment concentrations exceeding about 40 to 50%, and the remainder of the flow's volume consists of water. By definition, debris includes sediment grains with diverse shapes and sizes, commonly ranging from microscopic clay particles to great boulders. Media reports often use the term mudflow to describe debris flows, but true mud flows are composed mostly of grains smaller than sand. On Earth's land surface, mud flows are far less common than debris flows. However, underwater mud flows are prevalent on submarine continental margins, where they may spawn turbidity currents. Debris flows in forested regions can contain large quantities of woody debris such as logs and tree stumps. Sediment-rich waterfloods with solid concentrations ranging from about 10 to 40% behave somewhat differently from debris flows and are known as hyperconcentrated floods. Normal stream flows contain even lower concentrations of sediment. Debris flows can be triggered by intense rainfall or snow melt, by dam break or glacial outburst floods, or by landsliding that may or may not be associated with intense rain. In all cases, the chief conditions required for debris flow initiation include the presence of slopes steeper than about 25 degrees, the availability of abundant loose sediment, soil, or weathered rock, and sufficient water to bring this loose material to a state of almost complete saturation. Debris flows can be more frequent following forest and brush fires, as experience in Southern California demonstrates. They pose a significant hazard in many steep mountainous areas, and have received particular attention in Japan, China, Taiwan, USA, Canada, New Zealand, the Philippines, the European Alps, Russia, and Kazakhstan. In Japan, a large debris flow, a landslide, is called Yamatsunami, literally mountain tsunami. Debris flows are accelerated downhill by gravity and tend to follow steep mountain channels that debouch onto alluvial fans or floodplains. The front, or head, of a debris flow surge often contains an abundance of coarse material such as boulders and logs that impart a great deal of friction. Trailing behind the high friction flow head is a lower friction, mostly liquefied flow body that contains a high percentage of sand, silt and clay. These fine sediments help retain high pore-fluid pressures that enhance debris flow mobility. In some cases, the flow body is followed by a more watery tail that transitions into a hyper-concentrated stream flow. Debris flows tend to move in a series of pulses, or discrete surges, wherein each pulse or surge has a distinctive head, body and tail. Debris flow deposits are readily recognizable in the field. They may make up significant percentages of many alluvial fans and debris cones along steep mountain fronts. Fully exposed deposits commonly have lobate forms with boulder-rich snouts, and the lateral margins of debris flow deposits and paths are commonly marked by the presence of boulder-rich lateral levees. These natural levees form when relatively mobile, liquefied, fine-grained debris in the body of debris flows shoulders a side course. High-friction debris that collects in debris flow heads as a consequence of grain size segregation. Lateral levees can confine the paths of ensuing debris flows, and the presence of older levees provides some idea of the magnitudes of previous debris flows in a particular area. Through dating of trees growing on such deposits, the approximate frequency of destructive debris flows can be estimated. This is important information for land development in areas where debris flows are common. Ancient debris flow deposits that are exposed only in outcrops are more difficult to recognize, but are commonly typified by juxtaposition of grains with greatly differing shapes and sizes. This poor sorting of sediment grains distinguishes debris flow deposits from most water-laden sediments types. Other geological flows that can be described as debris flows are typically given more specific names. These include lava. A lava is a debris flow related in some way to volcanic activity, either directly as a result of an eruption, or indirectly by the collapse of loose material on the flanks of a volcano. A variety of phenomena may trigger a lava, including melting of glacial ice due to volcanic activity, intense rainfall on loose pyroclastic material, or the outburst of a lake that was previously dammed by pyroclastic or glacial sediments. The word lava is of Indonesian origin, but is now routinely used by geologists worldwide to describe volcanogenic debris flows. Nearly all of Earth's largest, most destructive debris flows are lavas that originate on volcanoes. An example is the lava that inundated the city of Armero, Colombia. Yakulaup is a glacial outburst flood. Yakulaup is an Icelandic word, and in Iceland many glacial outburst floods are triggered by subglacial volcanic eruptions. Elsewhere, a more common cause of Yakulaups is the breaching of ice-dammed or moraine-dammed lakes. Such breaching events are often caused by the sudden calving of glacier ice into a lake, which then causes a displacement wave to breach a moraine or ice dam. Down valley of the breach point, a Yakulaup may increase greatly in size through entrainment of loose sediment from the valley through which it travels. Ample entrainment can enable the flood to transform to a debris flow. Travel distances may exceed 100 kilometers. Damage prevention. In order to prevent debris flows reaching property and people, a debris basin may be constructed. Debris basins are designed to protect soil and water resources or to prevent downstream damage. Such constructions are considered to be a last resort because they are expensive to construct and require commitment to annual maintenance. In popular culture, in 1989, as part of his large-scale piece David Gordon's United States, and later, in 1999, as part of Autobiography of a Liar, choreographer David Gordon brought together the music of Harry Partch and the words of John McPhee from The Control of Nature, read by Norma Fire, in a dance titled Debris Flow, a harrowing taped narrative of a family's ordeal in a massive LA mudslide.